Good morning and welcome back to my YouTube video series on linear algebra. In this video, we're going to talk about the concept of norm. Um, it's a concept where you have a set, and your set has a lot of entities in the set, and we're going to focus on the vector space here. And a norm is a tool or a measuring system that you can come up with so that you can talk about the size or the magnitude of these entities. So before we begin, let me remind and maybe review about the concept of vector space first. A vector space is a set that has a nice property that is closed under vector addition and the closeness property under scalar multiplication. So in order for that, of course, you're going to need a concept of a sum between two vectors in vector space and a concept of scalar multiplication that is defined on a field. And um, now you can talk about a field of a real number. Okay, so this is a property of a vector space. What we have seen from linear algebra, the elementary class, is that the common sets that we see a lot in application, for example, Euclidean space, a set of matrices of size m by n. All these things are vector space because you make a sum of two vectors, Euclidean vectors, you still get the Euclidean vectors. You multiply a Euclidean vector, it still belong to the set of Euclidean vector and so on. All right, so these have closeness property under addition and scalar multiplication. And what else? A set of continuous functions on the support interval a and b, or the set of polynomial of degree less than or equal to n. Okay, and review that vector space, a vector space could have a subspace. A subspace of a vector space is basically a subset that the set M itself a vector space. So think about the special case, for example, in R2. In R2, if you only talk about a Euclidean vector that the component x1 is 0, all right? So um, so any x that the component x1 is 0, so x2 can be anything, all right? This set is a subspace um, because if you have a form of vector x and y in this that belong to this set, if you if you make a linear combination for any alpha in R, you will see that the first component is still 0. All right, which means this guy is still in your set M, and that shows the closeness property. So this set is a subspace. Okay, or you can talk about the set of diagonal matrices of size n by n. So the set of diagonal matrices is obviously a subset of Rn by n, and it has it's closed. This set itself is closed under addition. Make a sum of diagonal is still a diagonal. It's still close under scalar multiplication because when you multiply any alpha with the diagonal matrix, you still get a diagonal matrix. Okay, so this is just to review the concept of vector space. Any members of a vector space is called a vector. So today in this video clip, um, we would like to introduce the notion of a norm. So you can think of a norm as a transformation that map from your vector space, any vector space V, to a real number. All right, and we use this bracket, this like double line as a bracket, as a notation for a norm. In order for any transformation that has a mapping like this to be a norm, it has to satisfy three properties. Um, first of all, it's called homogeneous property. So what it means is that if you multiply x, you scale it with a scalar alpha. When you measure the norm of scalar multiplication, it's going to be the same as absolute value of alpha times the norm of x. Well, if I make an example of a Euclidean vector in Rn, so suppose this x, so minus 2x is going to be something like this, right? So you want to have a measuring system. Now, this is measurement system, which is a norm. They say that the length of the vector minus 2x should be 2, which is the negative absolute value of x, right? Which means the size, the direction of the x shouldn't, I mean, when the direction of x is flipped to the negative 1, it should not affect the size of that vector. All right, so this is homogeneous property. Second of all, it must obey the triangle inequality. The norm of the sum is less than or equal to the sum of the norm. So in Rn, we have seen this property because we know that when this is x, this is y, um, the vector x plus y is here, right? And everyone knows from the parallelogram law that the size of this guy, which is the norm of x plus y, is going to be less than the sum of this side plus the sum plus the side of this plus the width of this side. Okay. Last, positive definiteness property. A norm must be non-negative. Because we're going to use the concept of norm as a size, as a, to tell that, oh, this entity is big, is small. So it's the range of this mapping should always be non-negative. And it can only be zero when that entity itself is zero. Okay, so this is the third property. Um, so what I'm going to show here is examples of norms. It's this is all expression that you already know from application. For example, Euclidean norm, so it's a sum square take the square root. The one norm is a sum of absolute value. Infinity norm is the max of absolute value. Real quick, if I put x, negative 2, 0, 3, the norm 2 would be square root 4 plus 9, which is square root 13. The norm 1 should be should be 5. Infinity norm should be should be 3. That's it. Okay. Um, and all these norm functions are already implemented in any software, MATLAB, Python. You can just call it, but you have to call the option correctly, whether you specify one norm, two norm, or infinity norm. Um, I can show you real quick why some of this is a norm. Okay, let me put some easy example. What about the L1 norm? Why is it a norm? First of all, is it true that alpha x1 is it's equal to magnitude of alpha times norm of x, norm 1 of x? Is it true? You can see that obvious. This is obvious because this is going to be the sum of absolute xk, right? And that's simply, you can just take out the magnitude of alpha. Okay. Oh, maybe. Okay. Second of all, triangle inequality, the norm of x plus y, the norm one of x plus y. So it's going to be the sum of absolute value of xk, yk. Okay. But because you know that the absolute value of two real numbers, this is less than the sum of absolute value. Basically, we have a triangle inequality for a real number, right? This is very well known. And that's one norm of x plus one norm of y. Okay. Um, last. Is it uh, is it clear by the definition itself that the one norm is always non-negative, right? But how about when the one norm of x is zero? It means all the sum of absolute must be zero. And isn't that clear that because the sum of absolute values are the sum of non-negative values. So if the sum of non-negative value is zero, each term must be zero. When each of the absolute value is zero, that's only true when the vector x itself is zero. Okay, so um, a lot of things you already see from applications can be shown to be satisfy the concept of norm. Okay, and I would like to extend the concept of vector norm to a matrix norm. So first of all, when you have a matrix A that is rectangular, the the norm of A subscript F is called Frobenius norm. Frobenius Frobenius norm. Maybe you have to check the spelling. Um, what it says that you take A is going to be a matrix of size m by n. What you do is that you take all the ij entry of A, make the sum of all ij, and then take the square root. You see that the definition of the Frobenius norm is nothing but just apply the vector norm to the vectorized version of A. Like suppose you have A that is 1, 2, 3, 2, 5, -5, something like this. It's gonna be if you do the vectorization or uh, you flatten the matrix. The vectorized version would be 1, 2, 3, 2, 4, -5, right? Either you concat along the columns or you concat along the row, it doesn't matter, vectorization. And if you apply the Euclidean 2 norm of this vector, it's going to be the same as this formula. All right, so this is just the generalization how you define a matrix norm based on the concept of the 2 norm of a vector. So we have a similar definition for one norm of a matrix. Just make the sum absolute. Just make the absolute sum of all the entries. And for infinity norm of a matrix, you just take the absolute of all aij and then take the maximum one. In this example, In this example, norm one of this metric would be 1 plus 2 plus 3 plus 2 plus 4 plus 5. And the infinity norm of A would be 5 because we just take the maximum absolute value. Um, After we see example of L1 norm, L2 norm, L infinity norm, in fact, we have we can define an LP norm where the definition of the P norm is very similar to this one. Okay, it seems like you replace this power and the root here by the values of P. So the P norm, the definition is the following. You take the sum of the pth power of each term and then take the pth root after that. For example, when p equal 1/2, the 1/2 norm is going to be the sum of every term square root and then take the pth root, which is going to be square. Okay, so this is an example. And this p can be non-negative number, can be a real number as well. For example, the 1/2 here. And now let's talk about the concept of describing a set of all x that they all have the norm less than a unit one. Let's first introduce the set that all the vector x has a unit norm. And you know that this set, it just includes the area inside the set on the right hand side. So the question is the following. Suppose I have the norm x that I'm going to measure its size by the two norm, right? I want to explore other choice of x, other choices of vectors that have equal have equal norm to x, and that's why we are interested in this set. For for two norm, you know that it's going to be the set that um square root of some square is less than 1, all right? So it's going to look like a circle, right? And for this set, it means that you include only the points on the boundary. For L1 norm, it's going to be the set that absolute value of x1 plus absolute value of x2 is less than 1. And if you just in order to describe this, you just need to work with the absolute value. So you can use the simple fact that the absolute value can be split into x1 and minus x1 depending on the its sign, right? And if you just plug that in for all combinations of x1 and x2, you will end up having this area like a diamond shape. For infinity norm, uh, it's a set of x that the max of sk less than 1. But if the max of absolute less than 1, all the absolute value must be all less than 1. Both x1 and x2, its absolute value must be less than 1. So you're going to have a square box in the shape of the unit number of the three sets. And when t equals 1/2, this I use the computer to plot this. So it seems that it looks like a diamond shape, but the side of this is squeezed so that the king here becomes even sharper. Okay. Um, That's some related question is gonna be, very related to the concept of convexity of a function, convexity of a set. If I mention this real quick, is that you would see that all these sets have a convex curve, have a convex shape in terms of a set, and that's because L1 norm, L2 norm, L infinity norm is a norm. Okay. But this set is not a convex set because we will show shortly that the L1/2 is not actually a norm. When you decrease p from 1 to 1/2, 1/3, 1/4, all the way to 0, for L0 we have defined the norm as the cardinality of x. Okay, that is cardinality of x is the number of non-zero elements in x. For example, x is 2, -3, and 0. And L0 norm of x is 2 because there are two non-zero elements in x. The zero norm is not truly a norm in the strict sense that we just learned. There are three properties: homogeneous property, triangle inequality, positive definiteness property. So let's think about let's check about this condition again. Is zero norm truly a norm? Let's talk about homogeneous property. Um, suppose x is 1, 0, 0, and obviously zero norm is 1, right? What about negative 2x, which is -2, 0, 0? What about the zero norm of negative 2x is the number of non-zero elements. So it is still 1. But then it doesn't satisfy the homogeneous property because the in order for that norm to be a norm, negative 2x is supposed to be equal to the absolute value of -2 times the zero norm of x. So this condition is violated. All right. So that's why zero norm is not a norm. It seems that you can check other conditions as well for positive definiteness, the true norm, the zero norm is satisfied. Okay. What about 1/2? When p equals 1/2, it violates the triangle inequality. In this example, the vector 1, 2 and the vector 1, 0 and the vector 0, 1, the 1/2 norm is going to be 1 square root of 1 plus square root of 0 and then make a square which is all 1. But x plus y is a vector 1, 1, right? So its p norm is going to be square root of 1 plus square root of 1 and then square. And that is 2 square, and that is 4. So the norm of x plus y turn out to be bigger than the norm of x plus norm of y. So it doesn't satisfy triangle inequality. Okay. So now we see some example of LP norms that is actually a norm in the strict sense when p equals 0 and when p equals 1/2. In fact, LP norm is only a norm when p is bigger than 1. Okay, whatever p that is less than 1 is not, it doesn't make LP norm a norm in the strict sense. What is the advantage of knowing the concept of norm? Okay, if you have a vector x and a vector y, we know that this is going to be the vector x minus y. So if we use the concept of norm to capture the size of these vector x minus y, we basically measure a distance between a vector x and a vector y, or basically the distance between 2 points in Rn. Okay. So that's why the concept of norm also imply a concept of distance. We can use norm as a distance function. So let me illustrate with this plot. Suppose you have 2 points on the plane, the red and the green. All right. So you can represent these red and green points by a vector. If we use two norm, of course, if you use two norm, you use Euclidean distance, right? So you measure this side, okay? For one norm, as you measure so suppose this is vector x, this is vector y, right? And this is vector y minus x. So basically one norm, what you're gonna do is that you measure x1 minus y1 plus x2 minus y2. For Euclidean distance, you measure x1 minus, sorry, I think I wrote it wrong. So the one norm is supposed to be, is this correct? X1 minus y1. Yeah, it's already correct. And for two norm, it's supposed to be this, right? So this is the distance between 2 points. For infinity norms, so it's supposed to be max of xk minus yk. So for L1, what you do is, this is what I wrote here is a vector of x minus y. Therefore, for L1 norm, you actually measure this width plus this width, and that's going to be L1 distance. Okay. So in order to go from x to y, you actually walk around the corner. You don't walk straight from x to y, just like when you use the Euclidean distance. For infinity norm, or what we call Chebyshev distance, you're going to measure this side and measure this side and see which one is maximum. In this example, it's supposed to be this width, right? This side. So the infinity norm is the width of this side. For p norm, if you use the concept of p norm, a lot of people use the term Minkowski distance. Okay. For one norm, people use in machine learning and everything. People use the term Manhattan or taxicab distance because because of the reason that in Manhattan, the layout is in a grid system. So in order for a cab driver to go from here to there, all right, they actually walk around they have to drive around the block. They cannot go, they cannot drive straight from here to here. Okay. What else? So when we use a norm as a distant function, yeah, it is imply this generalization that the distant value should be non-negative. And a distance should have a symmetric property that when you talk about a distance from going to y to x and x to y, it should be the same. They should be the same. So that's why in mathematics, a distance function can be explained as the idea of a metric. So let me just mention to the concept of metric space, okay, later, shortly. But before we go into that, I would like, when we use the norm as a distance function, a lot of time we have these kind of question in hand. So suppose you have a set, suppose this is a set, the yellow set, and you call this set C, and you have a point Y that lies outside the set. You have this question that I want to pick I want to pick a set in as a point in set X that is closest to Y. And I'm going to use the notion of norm to measure as a distance. So you can pose a question like this. I want to minimize the distance between X and Y for all the points X in C. Okay. So if you use the concept of, for example, if you use the notion of two norm here, so it's more like, okay, if my x is here, the distance it would be this far. If my x is here, the distance would be this far. Then which x that give me the minimum distance? You can see from this example that it's supposed to be this x, right? That give me the minimum distance. What you can think of, how can you get to this x star? As we mentioned before, that a unit norm ball is a set that a unit norm ball, if you look at on the boundary of the unit norm ball, is a set of x that they all have equals norm. So if I put y as a center and I draw a circle here with this radius, so this is a set of all the vectors that have the same distance to my y. Let's say the distance is 1. If I draw a bigger circle, everything that lies on the circle has the same distance to y. Uh, let's make an example that the distance is 1.5, right? So when I keep drawing this circle, if I enlarge this circle until I hit C, right? That would be the smallest circle that touch the set C. And wherever it touch the set C, it gives me the point X on C that has the minimum distance. All right. I can use this this concept to other notion of norm. Previously I used one norm. Now if I use, sorry, previously I used two norm, but if I use one norm, as we see from as we see from this result, the unit one norm ball is going to be a diamond shape. Again, if I draw a unit norm ball with a center at Y, all the points on the diamond boundary are, are all the vectors that have the same one norm distance to Y. And if I enlarge this diamond, it means that all the set of vectors that have the same distance to y, but now the distance is this width, right? And if I increase the size of this diamond, right? Until it's big enough, but not too big, it's big enough that the diamond shape touch the my set C. At that point, at that point at that point, I have found my x that has the minimum distance to my point y by using the one norm. And if you use the same concept, right, to infinity norm ball, it's going to be the same. You draw the square box, square box, square box. Okay, whenever it touch the set C, you found a point of x in C that has the minimum L infinity distance. What I want to point out is that suppose I have the set C that look like this in general. If you use this same idea and you draw and you have the point y, right? And you try to find the point of x that is closest to y by using one norm, two norm, infinity norm, you will see, please verify yourself. You will see that the point x2 that has the minimum two norm, point x3 that has the minimum infinity norm, and the point x1 that has the minimum one norm. All these points are not the same location in the set C, which means the problem of finding the point that has the minimum distance also depends on the choice of norm you use. Okay, and that's the whole idea. Now let's continue. As I mentioned earlier, that when you use the concept of distance to measure, how far of a point one to another point, this is this can be visualized into the concept of metric space. Again, metric is a mapping, but it's a mapping from Cartesian product space. Is the space vector space x cross vector space x is a mapping to a non-negative real number. It is used as a has the distance meaning of 2 points. So again, in order for a function to be a metric, it must satisfy three properties. First of all, definiteness. If you measure the distance between 2 points, if the distance is 0, that's only possible that that points are the same, that 2 points are the same. Your concept of distance should be symmetric, right? It doesn't matter whether you measure from x to y or y to x, it should be equal. Third, triangle inequality. If you measure x to z and y, right? If you measure sorry, you have x, you have z, you have y, all right? If you measure the distance between x and c, it should be less than or equal to measure the distance between x and y plus y to z. This is triangle inequality. Any vector space x that has a metric defined is called a metric space. And as you can see that whenever you have a concept of norm, you can always use the norm of x minus y as a distance function. So you can check, okay, this is you can check that actually you can define a metric using norm of x minus y always, and it satisfies all of the three properties. Okay. I think the first two property is clear by itself, all right, can be easily checked. The triangle inequality can be shown that is satisfied by the following. So the distance between x and z, all right, by the definition is norm of x minus z. And then, but because x minus z, you can write it as x minus y plus y minus x, you add and subtract. And because of the triangle inequality of the norm is less than this guy plus norm of this guy. And that is the distance between x and y. This is the distance between y and z. Okay. So this is to show that you can always define a metric function that is the norm of x minus y. Mhm. It has a lot of interesting topics regarding the distance. In applications, we can have questions like we can have a concept of distance from what we see, or we already see a concept of distance between 2 points, Okay, we already see the concept of a distance from a point x from a point y to a set in this slide is a set M. Okay, so the distance between a set M to a point x, let me use the same notation, is actually use the concept of distance between z to x, but you're gonna pick the z that give me the minimum or the infimum distance. So this z doesn't give me the infimum distance. This z doesn't give me the minimum distance until you find this z. Okay. So we're gonna use the measurement, the distance between this z to this x to define as a distance between this point x to the whole set n. Mhm. You can also talk about the distance between two sets. Suppose you have set C, you have set D. Okay. So the concept is to measure the distance between 2 points, but X belong to C, but Y belong to D. Okay. So we find a pair of X and Y that give us the minimum distance. This is not this pair, this is not this pair, this is not this pair, but it looks as if, okay, in this example, it looks as if, oh, it's this pair of x and y that give me the minimum distance. So that define the distance of two sets. Mhm. So when you replace the distance function by using the concept of norm, okay, that can be seen in application as well. Okay. Last, okay, we can use the concept of distance to measure mismatch error between two entities. In numerical computations, suppose you somehow in your code or in your, I don't know, purpose of your calculation is you're going to have x and y that is equal in a mathematical sense somehow. But then in numerical computations, if x and y are kept as float, they are not going to be equal exactly, right? So you can use concept of norm to say that I'm going to measure the discrepancy between these two vectors, these two arrays, and it's going to be very close to zero, but you can just compare it with a threshold number. So instead of checking like if the whole array that are equal, they're not going to be equal in computer if both of them are kept as floats, right? So what you do is that you subtract one from another, and that's going to be a vector that, I mean, in the entry is going to be very close to zero but not exactly zero, and you use the concept of norm to measure the size of this error. All right, this concept goes the same when you have worked with matrices. Okay, instead of checking A equals B exactly, you measure the distance. And as you can see that if you use the concept of norm to measure the error between two vector or between two matrices, the choice of norm may affect the computation. I would like you to go back to this formula of these norms, okay? And maybe you sketch the computation inside, how many flops is required and what operation is required. You will see that in order to compute one norm and two norm, it seems that you have to compute n times because of the square operation and the addition. So it seems that it's going to be in big O of n. However, when you compute infinity norm, it seems that you're going to find a maximum entries. All right, so it depends on the algorithm that you find the maximum entries. Um, Application of vector norm can be more. All right. Um, Now I have listed some of the common examples. What about the first one? Just find a vector that has the smallest norm measure by any norm choice up to your purpose, right? But my x stays in a set, hyperplane or convex set. Okay. So suppose I have a set C. My set C is here. So suppose this is the origin. Okay. Um, my question is that I want to find the minimum norm of x where my x lie in the set C. Okay. So whether what it depends on the choice of norm you use. For example, if I have two norm, um, so it means that it find you are looking for a point x in C that gives me the minimum distance to the origin. So it's looks like this point. All right. If my set C, all right, this is an example. My set C happen to be the set that ax equals y, right? It has a lot of meaningful interpretation here. So it means that your x, your variable that you're looking for, somehow, um, it makes this term a linear approximation to y. Like you want to explain y as the linear function in x, and you want to find that choice of x that has the minimum norm. Okay. So, for example, in application, you could have this kind of problem that find give me the minimum one norm of a vector x where my x is a solution to linear system. Okay. So y equals x, y equal ax is reduce this to just one hyperplane. It's going to be like this, something like this. Ax equals y, a transpose x equals y, and any point that lies on this hyperplane satisfy this condition. But you're looking for a point of x along this hyperplane that has the minimum one norm. So what is it supposed to be? Again, with the same concept, you draw a diamond shape around the origin, right? And enlarge it until it touches your set. So this point is supposed to be the point on the hyperplane that give me the minimum one norm distance. You see a row of distance function in K and N, K nearest neighbor. So when you draw the diagram between points, right? If you have a point x here, like sample here, so the nearest neighbor is the set of neighbors that give you the minimum distance. And in K and N, they have different several choices of distance, just like what we learned here, L2, L1, and so on. In terms of regression problem in machine learning or in estimation problems, usually we're gonna have what we have is we have a model, and this gives us a meaning of y hat. Okay, this y hat is aimed to be close to your actual y, your measurement. So what you're gonna have is you have vector y, you have vector y hat, and then you subtract y hat from y, right? This is the error term or the residual. And now the vector e becomes the error vector, and now you aim to measure the size of this vector e by either the concept of mean square error, which is the sum square divided by n, or MAE, which is sum of the mean absolute value, right? So of course, MSE is going to be related to 2 norm of the error divided by n. MAE is going to be 1 norm divided by n. Okay, so I mean, in general, whatever row function you use here is actually the concept of distance function, because now you measure the distance between y and y hat. And if you use MSE and MAE, that means you use the row function as the norm distance. As you use 2 norm as the distance between y minus y hat. Okay. And Yeah, and that's all for for this topic. We have introduced you the concept of norm, give you an example of vector and matrix norm, and the connection between using a norm as a distance function.